Hi everyone, I'm Ella, and I'm really excited to be talking about N+1, specifically in this session, so thank you, James, for hosting it. So at N+1, our mission is to build the new standard for RNA synthesis. And thankfully, I'm later in the day, so you all have heard really the issues of phosphoramidite chemistry. So it really is not set up to deliver on scale for the large patient populations. And ligation solves a lot of issues. You heard fantastic talks by a lot of different people. But at the end of the day, we're still stuck with the solvents and the waste and the restrictions that come with phosphoramidite chemistry. So at N+1, we're trying to make RNA a completely different way without the solvents. So we have made the easyRNA platform, which is an aqueous-based enzymatic platform for synthesizing RNA. We don't use a template, so we can access the site-specific modifications that are in siRNA and ASOs. And we have been really focused on making our platform have really good cycle efficiencies, really good purity, because we've been thinking a lot about manufacturing, really what this whole session's about. And so because we are aqueous-based, we don't have any solvent concerns, we're not air or moisture restricted, and of course with the promise of really high purities. So the pyramid is currently unfinished. I will come back to that, but I'm going to start by sort of orienting everyone on our platform and how we've been looking at it through the manufacturing lens. So our platform involves 3 core components. We have a universal enzyme that incorporates all of the nucleotides, natural, standard siRNA modifications, and some other new interesting modifications as well. Our building blocks, like I said, are nucleotide triphosphates. They are blocked on the 3' with a reversible terminating group. They're otherwise protecting group free, and they're deblocked really mildly without any scarring. And then lastly, we do our synthesis on a solid support, so we put our growing oligo onto a resin bead. So in this case, we use agarose. I love the solid support. It's very aqueous compatible, and it's, of course, biomolecule compatible, which needs to be with our enzyme. So we put all of these core components into our cycle, and then out comes a variety of different things depending on what comes in and what we want to get out of it. So full-length product, we make siRNA-length oligos. Because the success of ligation, we've been focused a lot on making blockmers, so shorter strands of RNA. And then we also can tune RNA. So this is an interesting concept where we can take an RNA intermediate and we can add the last couple of nucleotides. So mRNA is a really interesting place for this, where we don't have to synthesize all 4,000 nucleotides. We can synthesize, we can get it from in vitro transcription, and then we can add the final couple of nucleotides or a delivery ligand. And this is where phosphoramidite can't really compete, just because it can't deal with natural fragile RNA. So for this talk, I'm going to focus on blockmers and how we've been looking at the synthesis of blockmers really through a ligation lens. And I'm going to start by orienting everyone on the platform itself and our cycle. So everyone needs to pay attention, because I'll come back to this ad nauseum. So we have our oligonucleotide that we call an initiator, or N, and this is because our enzyme needs to grab on to something to start synthesis, and then it's covalently linked to an agarose support. We then undergo an extension step with our building blocks and our enzyme. The enzyme will form the phosphodiester bond. We don't get any extra extensions because of the 3' blocking group. We have a couple of different ones, but no matter which one we use, our D block is the same mild condition. We form the N+1 product, if anyone was curious where our name comes from. And then we can undergo the cycle as many times as we would like to get the oligo that we desire. And then when we're done with the oligo, we can cleave it from the resin. And here in this cycle, our initiator and our nucleotides are natural. We can do natural. We tend to work with the siRNA modifications, and that's what you'll see in this talk. So here is an HPLC trace of an extension. So an N+1, the main peak is the N+1 with an asterisk on it. And here would be a coupling efficiency greater than 99%. We don't see any leftover initiator. And then depending, or not depending, no matter what, our D block is quantitative, so no matter which blocking group we use. And so we don't see any leftover N+1 asterisk product. Okay, this is fantastic. So why am I up here? Well, if we were to average these two numbers, we would still get a cycle efficiency above 99%, right? So that's fantastic. But when it comes to actual synthesis, the sequence itself matters, and so you're gonna get variability in your cycle efficiency. So I'm gonna tell you the story about block number 12. So block number 12 is 10 nucleotides long. It has a 5' phosphate, so it's ready for ligation. It has all of the 4 RNA building blocks. It has 2' methoxy fluoromods, and then it ends in 2 phosphorothioate linkages. So we synthesized this almost a year ago now, and this is what the trace looks like. So the main peak is the target peak, and we have a 97% cycle yield. So for a first synthesis, this is good, this is fine, but it's not the 99% that we had seen in the previous slide. And this is because, you know, a model is only as good as a model. Really, we see sequence variability, and we also see some nucleotide variability. And so what we typically do is we'll do a first pass synthesis or an evaluation synthesis, and we will essentially look at the impurities of the final product, and then we can do another synthesis to optimize the impurities that we did see. So looking at these impurities, I'm gonna start with the one on the right. We have target plus U-methoxy. So it's a pretty big peak of an extension product, and so we shouldn't really have this going on in our reaction, so we need to probe what's going on. And then on the left, we have target -1s, so sort of deletion products. We have -G-fluoro, -G-methoxy, and -C-methoxy. So given these takeaways, what we would do is we would optimize the incomplete couplings on the left side. We would try to reduce the reaction that's causing this addition product, and then we'd repeat the synthesis with the more optimized conditions. So we have done this iterative process for a lot of different blockmers, and there are patterns that we are starting to see emerge in our platform. So looking at this oligo almost a year later, this is exactly the trace that I would have predicted. G-fluoro, G-methoxy, C-methoxy are all nucleotides that tend to have a lower coupling efficiency. And then the impurity on the right is coming from a side reaction that was rearing its head in other ways, and so we had to end up solving it. So what I'm going to talk to you about today is sort of the patterns that we have seen in our synthesis and sequence context and nucleotide context, and how we have sort of the toolbox that we have made to solve each of these problems. And so now we feel that we have a really robust platform to be able to make an evaluation synthesis, our first synthesis, really, really good. So I'm gonna walk you through that. So making the first synthesis a good one, this is a slide we'll come back to a lot, and I'll lay out sort of the obvious things. We wanna have really high purity. So we wanna have sort of average high cycle efficiencies. We wanna decrease impurities, so reduce any side reactions. And then because these are all going into ligation reactions, we wanna have a really good handle on the purity profile, and we wanna have a tool to be able to control any impurities that end up being consequential in a ligation reaction. So I'm gonna start with purity. So purity, because our D block is quantitative, we really focus on coupling efficiency and getting that to be as high as we need to. And coupling efficiency, like I said, is dependent on two things: the actual building block that's being incorporated onto our oligo, and then the sequence of the oligo itself. And this is not only sort of coupling partners, but also structure, if any secondary structure is forming. So I'm gonna tell two stories about sort of preference, good and bad, of nucleotide and also sequence, and then the solutions that we have used to solve these. So I'll start with nucleotide. Here we have two HPLC traces of the exact same synthesis, so the same conditions, the same scale, and it's coupling onto the same initiator. But the difference is the building block itself. You have a U-methoxy on the left and a C-methoxy on the right, and you can see there's a 20% disparity in coupling efficiency. So we have a large toolbox of things that we can use to optimize our coupling efficiency. Time and temperature are probably the more obvious ones. We have more sophisticated ones as well, and it usually ends up being a combination of these things to get our coupling efficiencies up to 99%. In this case, we ended up being able to change the 3' blocking group, and so now this is a red blocking group. And we were able to increase our efficiency up to 99%, so similar to U-methoxy. And so this was sort of a silver bullet for us, which is great. It's not always like that. But more importantly, this is actually a pattern. So C-methoxy tends to be a little bit more of a troublesome child. And now every time we see a synthesis, we know to use a C-methoxy with the red blocking group. And so this has been a great, nice tool to have. Okay. Same story, but now with sequence bias. So now we have an A-methoxy PS incorporating onto almost an identical initiator, the difference being a U-methoxy and a C-methoxy is the terminal nucleotide. And you can see a difference of 24% in coupling efficiency. So we went back to our optimization toolbox. And in this case, it really was a combination of things. We also added a reagent that improves the activity of our polymerase. And so again, now when we see C-methoxy coupling onto an A-methoxy PS, or I think the reverse, we now know to use these optimized conditions, check mark. And so C-methoxy and then this example are just two stories of, Billy? There we go, okay. Thank you, Billy. So those are just two examples of biases that our platform has and then the tools that we've had to essentially come up and solve them. And so now whenever we go into a new blockmer, we have a much more informed synthesis. We know what the problem areas are gonna be so we can implement more optimized conditions. And then for any lingering coupling issues, we have that same toolbox. We have a lot of different things that we can use to further increase cycle efficiency. Okay, that didn't end up being the whole story. So even with quantitative D-block and with really good coupling efficiencies, our purity wasn't really where it should be, and that's because of the side reaction going on that I had alluded to. So let me tell you what I'm talking about. So going back to the cycle, we are now coupling a C-methoxy onto an oligo. We're using the red blocking group here, so we have really, really good coupling efficiency. But, I can use my laser, we have two peaks at the base of the target. And so when we go to do, when we analyze their masses, we see the one on the left is a target minus U-methoxy, and the one on the right is plus U-methoxy. So the first thing we'll notice is now in our model system, in a simple N+1, we're seeing the same addition product that we were seeing in oligo 12. And then we're also seeing what would look like essentially a deletion product. And so even getting coupling efficiencies up really high would still leave what we would assume are deletion products. But it looks like there's some reaction going on. So we need to fix it. Where is U-methoxy coming from? We did not give this reaction any U-methoxy. But if anyone caught it, it's on our initiator. So it's the terminal nucleotide of our initiator. And so what might be going on is the U-methoxy from the left oligo is being taken and put onto the right oligo. So we needed a solution that was hopefully sequence agnostic and we could just throw into our synthesis to reduce whatever was going on. And when we went to do some research, we found very little on enzymes of our type, which are template-independent polymerases. But we did find an interesting activity that template-dependent polymerases do. So enzymes that will read a DNA template and make DNA or RNA. And this is called pyrophosphorylases. So in both our synthesis and templated synthesis, we make a phosphodiester bond on an oligo. We generate pyrophosphate. And then a templated polymerase can catalyze pyrophosphorolysis, where the pyrophosphate will attack the growing oligo strand. In our case, it would be, In our case, if I can go back, it would be any leftover initiator, and then we would form a truncated product, and then we would form the triphosphate of the NTP that we just kicked off. So with templated synthesis, this is not consequential at all. The sequence is determined by the template. You have all the unblocked nucleotides in solution. And so it's not really an issue. But for us, this is detrimental because now we have two different nucleotides in solution, one of which is unblocked and can further react. And then we have two different starting materials now. So we do, in fact, form our target, but we'll also form essentially every reaction of these sort of four components. And so, to quote Bob Langer, we found a really good way to make this really bad. And so this is what a trace would look like if we were to really, really push the reaction or this pyrophosphorylases activity. So we'd have our target peak, and we have our N+1 peak, and then we have minus and plus emethoxys of both. But if pyrophosphate really was the issue, there's an enzyme called pyrophosphatase, or IPPase, that will degrade diphosphate into two monophosphates, and monophosphates are innocuous in the reaction. So we were, after making sure we were able to put it into our reaction and it didn't affect its own activity and it didn't affect the activity of our own enzyme, the same exact trace now looks like this. I was expecting an applause, that's fine. So our hypothesis was correct, that it really was the pyrophosphate, and then we were able to spike in this enzyme without hurting our reaction at all, and decrease all of our impurities. Okay, so giving us our second check mark. This is great. We were able to reduce some N+1s and some N-1s, and so our purity is on the up. And then for any lingering impurities, we really want to make sure that we're able to have a handle on anything going into a ligation reaction. And so we know that some things are enriched, but there are impurities that may end up in the ligation reaction. So we turn to industry, which uses capping. So it caps the 5' hydroxys of any incomplete couplings. And so when we implemented capping, we wanted to use the same tools that we already had, which is an enzyme that can make a phosphodiester bond. So we do our N+1 extension step. If we don't have 100% coupling, we'll have some leftover initiator. We can then perform a capping step with our enzyme and some sort of triphosphate that has a group that can be extended off of or can't be deblocked. And then we can continue on the rest of the synthesis. This cap needs to be very efficient. It needs to be essentially one of the most efficient ones we have because it needs to be able to cap what the other nucleotides couldn't. So finding this cap was not trivial, and I don't have time to go into it, but I'll just tell you we found a great one, and then we applied it to a short synthesis. So here we have an oligo, our initiator strand, and then we just added 5 nucleotides to it. I want to note that when we did this synthesis, we intentionally tuned our synthesis to only have about 95% coupling efficiency. We intentionally wanted 5% of initiator left so that we could actually cap and see how it was working. And we did 2 syntheses side by side. We did one that was uncapped, so our cycle as normal, and then we did one where we capped after every coupling. So these are what the 2 traces look like. Both of the peaks are target. On the left, the uncapped synthesis looks like there's a little bit less peaks, but there's a shoulder, and that's where all of our impurities are, and it's the exact impurities that we expected. It's essentially the target -1. On the right, we have 4 adorable little peaks, and all of them correspond to our truncated product plus a cap. And so we were able to show that in a synthesis, we get really, really efficient capping, and we're also able to move our impurities by about 2 minutes here. So we were really excited about this, about having another tool. I've given us our last check mark, but I want to note that capping after every cycle or after every coupling is not necessarily our end goal. We would most likely, after a ligation reaction, we get the results back and we say, hey, this one target -1 is really the issue, and so we can cap very specifically after that coupling. And so I want to show you another evaluation synthesis that we did, much more recent, where we included all of these tools. So we identified the difficult nucleotides and the couplings. We applied the optimized conditions. We added IPPase in, and then we did some more specific capping. So this is block more 27. It's also 10 nucleotides long, it's ligation ready with the phosphate, and it has all the mods, and this time it starts with 2 phosphorothioate linkages. In doing a first pass analysis, there's no secondary structure, so we don't have to deal with that. The difficult couplings, we noted and we implemented the optimized conditions that we had found. And then the difficult nucleotides are G-methoxy and C-methoxy. So for C-methoxy, we used our red blocking group. For G-methoxy, we weren't as worried about the first G-methoxy in the sequence because a good rule of thumb is that an N-1 at the 5' won't get ligated. But we were worried about the other G-methoxy, which is the 7th nucleotide, because it's getting away from the ligation site, and so we wanted to make sure we capped that if it did an incomplete coupling. So this is what our trace looks like. We, off the bat, our main peak is the target peak, and we have a 99% cycle yield. And so what we did was essentially use our tools, and we paid a lot of the upfront costs with optimization just by having a really, really robust data set. But we know we can do better, so what do? Well, we look at our impurities. So our impurities on the right will start with we still have a little bit of target plus C-methoxy. It's much, much reduced, but we know that we can just increase our pyrophosphatase concentration and really decrease that impurity. And then on the left, we have a target minus C-methoxy, so even the red blocking group wasn't enough. And so what this tells us is that C-methoxy onto the U-methoxy in this particular sequence context is maybe more difficult, so we would optimize those conditions. And then the target minus A-methoxy was a little bit more surprising. A-methoxy tends to be a really good nucleotide for us. But again, this just tells us that A-methoxy onto the U-methoxy, so this A-methoxy comes from the 4th nucleotide. And so coupling onto that U-methoxy PS was a little more tricky, so again, we would optimize it. And then finally, we have the N+6 plus cap. The 6th nucleotide is the C-methoxy. We coupled G-methoxy. It didn't go all the way, so we capped it, and we're able to not have any minus G-methoxy and -1s here. So with these takeaways, our next steps would be to optimize the difficult couplings, to put it into a ligation reaction to understand if any of these impurities are consequential, and then do another capping step. And then we would repeat the whole synthesis, again, with more optimized conditions and with pyrophosphatase concentration. So we're really happy with where our platform sits, sort of even at the first pass evaluation synthesis. And then just for fun, we compared this to a phosphoramidite standard. A starting cycle yield of 98.3%, so it's good, but we do outcompete. And then their purity profile is also not great. A lot of the impurities are eluting, similar to the target. I do want to note that both of our syntheses can do better. This is, again, just a first synthesis for both. And we can optimize our sequence like phosphoramidite can optimize theirs. But overall, we're really excited about where this stands. So I'm going to move away from chemistry and talk a little bit about what our process looks like. So we use loose resin, and we stir our resin during a reaction. About a year ago, we were in a packed bed column, and it was really giving us a ceiling for coupling efficiency, for load. We couldn't densely pack our resin, and then also scale. Moving into a loose bed, or a loose resin in a stirred bed format has really allowed us to hit the metrics that we need to hit. It's allowed us to hit scale milestones. And then we also can sample our resin now that you couldn't do in a packed bed, so we can track and see how the synthesis is going. Our process is really simple. Again, we're not moisture or air sensitive. We equilibrate the resin, we do an extension, we wash, we do a deblock, and we wash. And then because of the sort of how really amenable the loose resin is, how high it can load, and how simple the process steps are, we've actually made really great progress in scale. So a year ago on packed bed, we couldn't break microgram scale. Today, we're at 100 milligrams, and in this year, we're getting to gram scale. And I want to say scaling has been incredibly linear, and so we can expect that we're going to keep some good momentum. OK, bottom of the pyramid is done. We have a great platform. We can do manufacturing. And now I want to talk a little bit about how our platform can also be used to access new and interesting chemistries, all with an eye towards therapeutics and the next generation. That's a far way off. So I'm just going to talk about modifications. A quick overview, we have inclisiran here. Modifications make RNA therapeutics, stability, PK modulation, reducing immunogenicity, and a delivery ligand speaks for itself. So despite how important these modifications are, in the FDA-approved drugs, there's only 12 modifications. And of course, phosphoramidite can do more. There are great papers being published every day. But it is just showing that P3 is inherently a very harsh chemistry, and so we are limiting ourselves in what we're able to do. For example, Nature has over 200 modifications. And again, while phosphoramidite can access some of them are really complex and fragile, and they would be really difficult for phosphoramidite. So we are trying to essentially push the bounds of what's possible, access the natural modifications, but then also see what else we can do. So here is a small set of modifications or modified nucleotides that we can do. We've broadly bucketed them into the therapeutic benefit that they can impart. I see people taking pictures. Please come talk to us after. This is just a small set. We've incorporated over 50 modifications. And some of these here are, again, totally easy with phosphoramidite, but some of them would actually be really challenging. And we have some new and novel modifications as well that I can't talk about. But I do want to talk about our work with vinyl phosphonate. So this is not novel to us, but in order to install vinyl phosphonates, it's very difficult. And if you do it internally, you have to make a dinucleotide. And so it's not as easy to sort of walk. And we thought this would be a great place to show how amenable our chemistry is. We can treat vinyl phosphonate just like another building block. So we made the nucleotide triphosphate of vinyl phosphonate. We put our 3' blocking group on it. And then we did an N+1. And we got really good coupling efficiency. This is actually a pattern. Our enzyme tends to be really amenable to backbone and phosphate modifications. And then to make sure that we could deblock it and we could extend off of it, because our enzyme can be sort of picky about what it extends off of, we did an N+2. And we were actually able to keep our coupling efficiencies up. Our deblock was quantitative still. So this was fantastic. And then to make sure we could put it internally, we incorporated 2 more nucleotides, an A-methoxy and a C-methoxy. And again, our trace still looks really great. So we're really excited about vinyl phosphonate, but really just as a little story to show really where we think our platform can be going. And I will end with saying when we're thinking about N+1, we're thinking about the future of RNA therapeutics and how we can build a platform that best enables that future. And this is both in terms of scalable manufacturing, being able to hit metric tons to meet the large patient populations, and then also pushing into novel chemistries to make even better drugs. So with that, thank you so much for listening. Thank you for chairing this fantastic session, James, and I'm happy to answer any questions. Thanks, James.
All right, looks like we got a question.
Yeah, just curious if you looked at glycol nucleic acids, so open chain ribose.
Yeah, we haven't tried that. We haven't pushed into sugar sort of ring modifications as much.
I'm expecting it'll be challenging.
Yeah,
For the phosphorothioates, do you get like stereoselective coupling or a mix or either?
Yeah, it looks like we are stereoselective towards the S. So Sarah Lovelock also showed similar data. So in the oligo, it ends up being the R configuration.